about it. So we start, Mariana? You wanna do an introduction, or shall I just begin?
You can go ahead.
Okay, great. So welcome everyone to the third and last day of this Young Frontiers meeting. Today, spoiler alert, presumably our speakers will wrap up and tell us about what they think are the most exciting research avenues that stem from this lecture. So keep your eyes peeled, interrupt, ask questions. And yes, let's get started. We will begin with Ignacio, who is talking about the quantum properties of relativistic stars. So Ignacio, your slides are already on. I can see them really well. I think I can hear you too. So
Super.
the virtual floor is all yours, whenever you're ready.
Thank you very much, Thomas. Yes, so let's start with the last lecture. So as yesterday, I'm going to start with a quick recap of what we talked about the last lecture. So one of the main ideas, we've been talking about the Buchtel limit, and as we discussed yesterday in the discussion session, one way to characterize the Buchtel limit is the point where the redshift of a signal that is traveling. So if we're talking about spheres, right, in general relativity. So the idea is that if you consider the propagation of a signal from the origin outwards, what happens at the Buchtel limit is that the redshift of that signal from the origin to any other point in the space goes to infinity. And this is exactly the same that happens at a black hole horizon. So that's why these two situations have many things in common. The other thing that we talked about is if you take the Fermi-Dirac distribution at zero temperature, you can look at the non-relativistic approximation where you get an equation of state that looks like this. Seems to be a bit lagged, maybe. Can you see my pointer?
Yes, we can.
Okay, cool.
It's like a laser saber. Is that what?
Right,
exactly.
Is that correct?
Yeah. Okay, awesome. Yep.
Okay, so this thing scales in the non-relativistic way, but we also saw that at very high energies, namely when the energy density is much larger than the scale determined by the mass of the particle of the fermion involved, then the scaling changes, and we saw that the equation of state took this form, where at leading order rho is proportional to 3p. So at leading order, the trace of the energy momentum tensor vanishes, and there are subleading corrections in this case that scale with the mass and are proportional to the square root of the density. And then something that is related to this, if you look at the Einstein equations, is that this very same fact of the fact that the trace is vanishing at leading order means that if you calculate the Ricci scalar and you compare it to other curvature invariants, say the Euler density, which we're going to talk more about today, the Ricci scalar is suppressed with respect to that one. And finally, we talked about the Oppenheimer and Volkov problem explicitly, and we saw that the main two results in that paper was that there was a maximum value of the mass for static solutions for this particular equation of state, which is of order 1 solar mass, and that there were two branches. So one branch which is stable, so all these solutions are static, but the ones on the low density branch, so before the TOV limit, before this point, are stable, whereas the other branch is unstable. And finally, we discussed that the last solution to the endpoint of this curve is precisely the Buchtel limit for this equation of state. So the plan for today is the following, and this is going to be basically based on a preprint that I put recently on the archive. We're going to ask the question first of, now that we understand these solutions better, we want to understand how classical fields, other fields, propagate in these spacetimes, and then consider quantum fields. So doing quantum field theory in curved spacetime for these particular solutions, and then understand what does that imply about the back reaction in the semi-classical Einstein equations. And finally, we're just going to look at a very particular example where we again go back to to the Buchtel limit and look at what happens for scalar fields. Okay, so by a regular star, we already talked about this, but to recap, we have this isotropic perfect fluid. The metric has two unknown functions of the radial coordinate. So one thing that we hadn't discussed so far, but it's very well known, is that for the solution to be regular, we need to impose some smoothness conditions at the origin. In the case of the metric, we need to require first that the our component, so this function over here, goes to 1 at the origin, because we really want to have a round sphere rather than something like a cone. And then we also need to require that the first derivatives vanish, right? That's how this is the definition of local flatness, right? Curvature is something that comes at second order. Now, if we require local flatness of this metric at the origin, you can very easily show that, and we're going to use this in a moment, you can very easily show that the square, this is the square of the Weyl tensor. Okay, so this would be like this thing. Okay, you can prove that this thing vanishes identically at the origin. Okay, for now, just take that as an observation. I'm not saying that the Weyl tensor, the components of the Weyl tensor vanish. I'm saying that if you take the square and you sum all these components, that thing vanishes at the origin. So let's start by looking at class how we've been talking about the geometry close to the Buchtel limit, but now the question we want to ask is, what if we now consider other fields that are propagating on these spacetimes? And we can start with the simplest example, so a massless minimally coupled scalar, which satisfies the Klein-Gordon equation. Again, this is the metric. So, of course, this is well known. If you decompose in the standard way, you separate variables in this way, you can recast the Klein-Gordon equation as a Schrödinger equation, provided that you change coordinates, you change radial coordinates to the so-called tortoise coordinate, which is defined in this way. Okay, it's just depends on the ratio of the two functions that appear in the metric. This is the same thing you do for black holes. You want a coordinate that moves slowly as you approach the horizon, and it's the same thing here. Now, if you do that, of course, the devil is in the potential. So for the spin zero case, so for the scalar field, the potential takes this particular form, which is not going to be very important, actually, but it's a very explicit thing. You have two terms. So you always have the centrifugal barrier, which depends on the angular momentum of the mode. And then you have something that depends only on the metric and its derivatives. Yeah, so we said that this coordinate R star is what's called the tortoise coordinate. So in the exterior of the solution, we always have the vacuum Schwarzschild. And in that case, right, this is in all of the textbooks, right? Since for the Schwarzschild case, we have that F is inverse H is equal to 1 minus 2m over R, it's just Schwarzschild metric. You can very easily integrate this equation and find what the tortoise coordinate is explicitly. And one thing that we always learn when we use the tortoise coordinate for the case of black holes is the fact that this thing ranges from minus infinity to plus infinity. So if we take, in the previous equation, if we take R going to infinity, clearly this thing goes to infinity because this one goes to infinity and the log actually also. Okay, so the torus coordinate goes to infinity at spatial infinity. But on the other hand, if you approach the horizon, so if R goes to 2m, you see that the first term is constant, but the second term diverges negatively because you get the log of 0, right? Going from above. So the important thing here is that the range of the coordinate, R star, goes from minus infinity to infinity in the case of a black hole. Now, what happens if we take a regular star? So a regular star, as we just said, satisfies the condition that h at the origin, the other function, the metric, has to be 1. This was the requirement of flatness. So if you look at the equation that defines the tortoise coordinate here, we can evaluate this thing at the origin. H goes to 1, and the only thing that survives is the square root of f, which is written down here. So, and then of course you get corrections, but those things are going to be subleading with the radius. But now you can remember that one of the defining features that characterize the Buchla limit is precisely that this function, which gives the redshift, goes to 0 at the origin. Meaning that in the Buchla limit, the variation of the tortoise coordinate with respect to the standard Schwarzschild coordinate blows up, right? Because this thing is going to 0, therefore this thing is going to infinity. So again, we see that in the Buchla limit as well, in the strict Buchla limit, you can also define a tortoise coordinate. It's given by a different formula than in the case of the Schwarzschild solution, because the metric is different. But in the Buchla limit, this thing also opens up from both sides, and it has a very similar behavior. So this is another way of seeing the similarity between the black hole case at the horizon and the Buchla limit at the origin. Okay, so now we said the interesting part of the physics is captured in the potential appearing in the wave equation. So here what I'm doing is giving a simple example where I went back to the constant density solution that we saw in the first lecture. And for a moment, let's just focus on the left side of the slide. So here what I'm doing is I am plotting the potential in the wave equation, in the associated Schrodinger equation, here on this axis, and this is the tortoise coordinate. So here we have 3 different curves. So outside the solution is always the Schwarzschild solution, which happens to have a maximum there. This would correspond morely to the light ring located at 3m outside the star. And then we have the solution inside the star. So as we already talked about, the solution, the potential becomes trapping. This is the same effect that was happening for null geodesics, or for light rays, as we saw, I think, in the first lecture. But now we're seeing a similar effect for the spin 0 particle. And what happens in the Buchla limit is that this potential becomes flatter and flatter in the origin. So the Buchla limit is when we're moving in this direction. Let me write that. So each one of these curves is progressively closer and closer to the Buchla limit, and you see that the potential becomes more and more trapping. In a certain sense, this is the same thing that was happening for light, because the minimum of this potential, which morally corresponds to the inner light ring of the solution, is just going to the center. And as we discussed, you lose the centrifugal barrier at this one you lose when you go to the strict Buchla limit. Now there's so we talked about the spin 1. So the photon, this happens for the spin 0. It also happens for spin 2. And this was actually worked out in a really nice paper by Chandrasekhar and Ferrari in the 90s, where they looked at the axial gravitational perturbations, and then you get the same effect. So actually this is the plot from their original paper. And what I wanted to stress here is that the really interesting part of this computation is that as the potential becomes more and more trapping, what you'll see is that there emerges a set of quasi-bound states. Okay, these are states that are not really bound states, right? Because the potential here at infinity goes to 0, whereas here, it has some finite value. But these are like resonances. These are states that can live semi-trapped there for a long time, quasi-bound states. And the point is that in the Buchla limit, when this potential really goes to 0 at the origin, the number of semi-trapped or quasi-bound states grows without bound. This is a completely classical calculation. Okay, this was for the spin 2 case. This is for the spin 0's case, and we saw the same thing happening for this spin 1. So this motivates one, or at least it motivated us. When you look at this picture, you cannot help thinking that this resembles a particle in a box, right? Such that there are more and more trapped modes there. So it's a very natural question. In a classical field theory, you can just decide to put all the fields to 0. So none of these modes are going to be excited. In quantum field theory, or in quantum theory in general, you don't have that freedom, because the best you can do is to just evaluate, put the system in the ground state, in the vacuum. And the vacuum is going to occupy these levels. So a very natural question to ask is, what happens if we do quantum field theory on the background of these on these kind of geometries? And we'll see that something interesting appears. So
Ignacio,
how can we do that?
Before you move on,
Yeah.
you're plotting here the classical potential, right?
Yes.
This is the expression you showed in the previous slide.
Yes. That's
What do you get at discontinuity? Well, in your case, it's close to 0, but in the other plots, it's
right. So
R equals to M or something like that.
This is the So this discontinuity happens at the surface, what we were calling R equals RB, the surface of the star. And the reason is because can you still hear me?
Yep.
Yeah. So the reason is that if you go back to the potential, you see that the potential contains these two terms. The angular term depends only on the function f, and f is continuous at the boundary of the sphere. But the other term depends on the derivatives, and we do not impose continuity of the derivatives of the metric at the surface, only of the metric itself.
You have to solve some other restriction, like an Israel junction condition or something like that?
Not in this case, because that would be the case if there was some kind of like localized layer, like a shell of material, right?
Okay.
Yeah.
Does this mean that the curvature blows up as well?
No, not at all. No. Not at all.
Okay.
This is similar. Look, this is very similar. If you would ask the question, so in this example, this occurs essentially because in this particular example, we took that rho was constant all throughout the sphere. So rho here inside the sphere is constant, but rho is just 0
outside. Okay, yeah.
Right?
You're putting it by hand, basically.
Exactly. In contrast, if you look at the pressure has some maximum value and then drops to 0 at the surface. That's the definition of the surface of the sphere. This is essentially the same thing that happens, in the surface of a lake, right? So the density of water here is different than the density of air outside, but the pressure here is the same pressure. The pressure is continuous, but the density is not. But that doesn't mean that there's some kind of singularity going on there. You know what I mean?
Yeah, I think I understand. Thanks a lot.
My camera turned off by some reason. I'm trying to fix that. Okay, so this gives us a motivation to study quantum field theory. In principle, you can just stick to the example we were looking at, consider the scalar field, find the modes, do canonical quantization or whatever, but that's a very long and painful calculation, and it's very particular. So there's another way to proceed, which is much more general, which uses only some very general properties of quantum field theory, and that's the story of the anomalies. So anomalies is very well known. Is the idea that a classical symmetry doesn't survive after quantization. The symmetry that we're talking about in this case, sorry, I'm trying to log in back with my camera. Okay. So what is the symmetry that we are concerned with here? The idea is very simple. Of course, it's conformal symmetry. There we go. Okay. So if you take a very simple example, if you take a particle in a box and the energy satisfies this relativistic equation, if we now take the limit where the momentum is much larger than the energy scale provided by the mass of the particle, then essentially the energy is just the momentum. Of course, there are subleading corrections that depend on the mass. Now, if you do a very similar computation in classical field theory, what this means is that if you take the trace of the energy momentum tensor, this thing vanishes at leading order. And this thing we were talking about yesterday. We don't need to require that this vanishes exactly, but the point is that the leading order will vanish. Now, and that's the behavior that, for example, we saw yesterday for the fermions. Now, there's one essential behavior or feature that exists in quantum field theory, but does not exist in quantum statistical mechanics, and that's the story of the anomalies. So in particular, we're going to look at the trace anomaly. So here I'm going to do everything in 3+1 dimensions. The statement of the Weyl anomaly is that on top of the trace, on top of the contribution coming from the classical terms, okay, so here I said this was approximately to 0, but of course there are terms that depend on the mass, and we're going to keep them. We're going to write them down in a second. The statement of the conformal anomaly is that on top of those classical contributions that normally depend on the mass, there are other contributions which come purely from quantum field theory. In 4 dimensions, the result is that there are essentially 2 contributions that are independent of the scheme of renormalization. The 2 contributions come with 2 coefficients, which are positive in this notation. So the first one is the square of the Weyl tensor, as we saw before. And the second one is the Euler density, the same one that we talked about yesterday. So these two coefficients are just fixed by the theory that only depend on the spin of the representation. They satisfy some nice theorems. They're very well understood. Notice, by the way, that there's one last term that sometimes people may add, which is a number times the box of R. The issue with this term, which is a bit problematic, is that this thing is scheme dependent. Okay, in contrast to the other 2 coefficients. So this term here is not fixed by the Lagrangian of the theory, and is it depends on the UV scheme that you're using to renormalize. So for the sake of of today, I just set this thing to 0. In principle, what we should do is to make an experiment, fix the value of this thing in our scheme, and then use that information, right, as usual, to make a prediction about some other experiment. But since we don't have any of that data, and it doesn't seem that we will in the near future, I'm just going to set it to 0. So in general, what we have is that the total stress tensor of the theory is going to contain 2 contributions. One contribution is what people normally would call classical, and the other contribution is what we might call quantum. Now, in reality, all the matter in the universe is quantum. So even what we call classical comes from averaging something that is quantum. But for now, let's just call it classical. The distinction between these 2 terms is that the first one breaks conformal symmetry already at the classical level, for example, having a mass, and it does not explicitly depend on the metric. On the other hand, the quantum contributions, these are the really hard ones to compute, contain the anomalous terms, and they, of course, depend explicitly on the metric via the curvature invariance. So again, the anomaly takes this form in 4 dimensions, where the Euler density is given by this thing over here. The Euler contribution is topological in the sense that this Euler density is the one that satisfies the Chern-Gauss-Bonnet theory in 4 dimensions. Okay, the one that such that if you integrate this thing on the manifold, it gives you the Euler characteristic of the manifold. The first one, the Weyl term, is not topological. Okay, so now I'm going to make a simple set of assumptions, and then we're going to do a very simple calculation, and we're going to see that something interesting emerges. So the assumptions I'm going to do is that, which I think are very conservative, is that if all the physics happening is much before the Planck scale, so say that, for example, the density is much smaller than the Planck density, or the curvature, the radius of curvature everywhere are much larger, right, than the Planck scale. So that we're far away from quantum gravity. I'm not interested in that. So I'm going to make the three following assumptions. The first one is that the semi-classical approximation is the right theory that governs the system. That means that the metric is classical. So the left-hand side of this equation is totally classical. And the quantum is the quantum fields are just on the right-hand side. The second assumption that I'm going to do is a statement about the behavior of the so-called classical matter, in particular about its equation of state. And now when I think now you'll understand why we were having this whole discussion yesterday. In particular about its equation of state at high energy. So the assumption I'm going to do is that if I take the trace of the classical part, then that if the density is much higher than the mass, the scale determined by the mass of the particles, this is what I would call ultra-relativistic, but still the density of energy is much smaller than the Planck scale, then that this trace, so rho minus 3p, this thing vanishes at leading order. And at sub-leading order, there are corrections that depend on some mass scale, that it might be the mass of the particle, for example, that was the example from yesterday, some mass scale m that appears here, and there's another number alpha, which you need to introduce in order to match up the dimensions, right? So in other words, I assume that this trace, there's no linear dependence with rho, because that thing cancels at leading order. There are subleading corrections which scale with rho to the power alpha, where alpha is strictly smaller than 1. And whatever the coefficient of that thing is, it has to have dimensions of mass in this way. That's what this mass represents. So basically, you can choose any theory you want. Find its equation of state. So find the relation between rho and p, and take this difference at very high energies and see what the remaining term is, because the leading term is always going to cancel. Find what the next to leading order is, and from there you read m and you read alpha. So for the example that we were talking about so far, for fermions, we had that m was just the mass of the fermion, and alpha was 1/2, because we saw that this trace was proportional to minus m squared times the square root of the density. This is what we talked about yesterday. So this is one very particular example. Finally, I'm going to assume that the quantum terms, the anomalous or the quantum terms, if you were to compare their contribution component by component of the stress tensor to the classical contributions, the quantum contributions are always subleading, are much smaller than the classical ones. These two things become of the same order naturally only at the Planck scale, but I'm not interested about that regime. That's not the interesting physics here. Okay, so under these assumptions, we're going to do a very simple calculation. We want to evaluate what the contribution of the trace anomaly is to the semi-classical equations. That's very easy to do. So the first thing is that we're going to, just for simplicity, we're going to restrict to regions where essentially the Weyl tensor squared vanishes. Okay, this of course doesn't happen always. It happens under certain circumstances, but we already talked about the fact that for a regular star, the Weyl squared at the origin vanishes. That's why I mentioned this before. Another obvious example of this is if you take cosmology, for example, take an FRW, then the Weyl tensor vanishes by itself. So that's another example. So let's restrict to cases where the square of the Weyl tensor is either very small or 0. So now I want to evaluate the only remaining piece in the anomaly, because if you remember the anomaly, the trace anomaly has two terms. One that comes with the square of the Weyl tensor, this thing vanishes, and then it has the other central charge times the Euler density. So now, since the first term doesn't contribute, we just need to evaluate the second. Now, to do this easily, we can use what's called the Ricci decomposition, which gives the Euler class in terms of some other invariants. So in this way, now you see the first term vanishes because it's the Weyl square. That sort of contains all of the Riemann tensor contributions. And then we only have two other contributions, the Ricci scalar and then the Ricci tensor square. So now we ask a very simple question. If we take one of these backgrounds that we have been talking so far, a background that, okay, what do I mean by background here? I mean the background given by this equation. So the background solution means that we consider essentially a solution that in our case would play the role of the Oppenheimer-Volkoff solution that we've been talking about. So we take the classical fluid. That's one contribution to the matter, and that thing generates the geometry. Okay, this could, in our example, this is the best thing to have in mind. We take the Oppenheimer-Volkoff solution that we've been talking about already. That provides the background, and on that background, we want to evaluate what the anomalous contributions are. Okay, it's a very simple calculation. So, as we talked about yesterday, if you take the trace of the Einstein equations in 4 dimensions, you get the Ricci scalar on the one hand side, and then the trace of the stress tensor on the other. Now here we have the trace of the background stress tensor. That's the fluid, right? And we already saw this is an assumption. This was our assumption 2, was that this thing scales as rho to the power alpha. And we know that fermions do this with alpha equals 1/2. On the other hand, we need to evaluate the Ricci tensor square. That's also very easy because from the same Einstein equations, right? We can just rewrite this thing as R mu nu is equal to basically G, the fluid contribution. That's the plus, and now let me throw this term to the other side of the equation. Okay, I'm just rewriting the Einstein equation. So here, okay, this is let's work here for a second. So here you see that when you now take the square of the Ricci tensor, you're gonna get a term that looks like this. This is the fluid contribution. And then you're going to get some cross terms. And then let's look at the last term, r squared over 4. Well, it's essentially r squared, right? So now you see, I hope you see where I'm getting to, which is that this contribution over here scales as this is rho squared plus 3p squared, because I'm taking the square of the matrix given by the energy momentum tensor, right? But on the other hand, this term over here, the Ricci scalar squared, this one goes as rho minus 3p squared. But we already know that this particular combination is the one that cancels, that is subleading at high densities, right? So this term, so now if I go back here, basically, with this small calculation, we see that the Ricci scalar grows as rho to the alpha, meaning that the Ricci scalar squared scales as rho to the 2 alpha. But the Ricci tensor squared is not suppressed in any way because it contains other combinations of the stress tensor, meaning that it contributes as rho squared. So when rho becomes very large, the point is that the Ricci tensor squared is much bigger than the Ricci scalar squared. Okay, this is a very simple consequence of the fact that the trace is vanishing at leading order, whereas the other combinations don't. So what does that mean? Finally, that when we ask the question, well, what is the biggest contribution to the trace anomaly? We see that the contribution comes from the Ricci squared, and if you plug that back into the trace anomaly, you see that this thing scales as rho squared, g squared rho squared. Okay, so now with that information, let's go back to the semi-classical Einstein equations. To the equations that we wanted to solve in the first place, right? That contained the fluid, the background solution, but also the quantum terms. And now we know that the contribution of the quantum terms, we know how it enters the equation, right? And that's what's written here in this last line. So we have that the Ricci scalar. So now I renamed just G as I put it back with a Planck mass. And then there are two contributions to the trace of the stress tensor. There's the classical contribution, which scales as rho to the alpha by assumption. And then there's the anomalous contribution, which scales as rho squared. So, and by the way, notice that this is very important, that the signs are completely fixed. So when you do this calculation at the end, you see that there's a relative minus sign between these two terms. This sign is completely fixed because in the trace anomaly, the contribution of the Euler term comes with a definite sign. You cannot change the sign. So in the semi-classical Einstein equations, there is a positive contribution that is suppressed at high energies, and there's a negative contribution that just has its natural scaling. So now you can ask the question, if I ask you now the question, well, if you start from the Oppenheimer-Volkow, say, computation, and you ask at which densities do the corrections coming from quantum field theory become relevant, macroscopic, the answer is whenever this term becomes of the same order of this term, right? And if you solve that very simple equation, the solution for this sort of critical density when this happens is simply given by this. Where to write it in a simple way, I factored out the Planck density here. So the density at which quantum field theory becomes macroscopic, that is of the same order as the source for the Ricci scalar, is not the Planck scale. It's another density, which is the Planck scale multiplied by this number over here. That depends only on the mass and the parameter alpha that appear in the equation of state. Now, again, going back to the example of the fermions, if you want to have an estimate for the order of magnitude, you simply, you just plug in the mass of your favorite fermion. Let's say you put the mass of the electron. And because the mass of the electron, and actually all fermions in the standard, all particles in the standard model, is so much smaller than for the fermions than the Planck mass, this number over here is very, very small because it's a small number raised to a positive power. Meaning that this scale, the scale at which this effect happens, is much smaller than the Planck scale. But this has nothing to do with quantum gravity. So basically what the Ricci scalar does is that at low densities, it is positive, as it is for normal classical matter, but at some point, the effects of quantum field theory kick in, they come in with a negative sign, and the Ricci scalar goes to 0 and changes sign. And notice that in this calculation, there's absolutely no room for doing any arbitrary choices. I fixed 3 + 1 dimensions, and the coefficients in the trace anomaly are completely fixed, except for the box R term that we put to 0. Apart from that, there's nothing you could change. So the upshot of this little computation is that if you ask the question of comparing the quantum contributions to the classical contributions, component by component in the stress tensor, when do they become of the same order? The answer generically is just the Planck scale. Then the theory fails, you need to use string theory, whatever, that's another story. But if you ask a different question, namely, when do the traces of the quantum and classical terms compete? The answer is not the Planck scale, it's given by this other scale, and it's much smaller than the Planck scale. Therefore, quantum field theory in curved spacetime is still valid in this regime. So finally, now that we found some interesting behavior of the semi-classical equations, now what are the physical implications? Can you do an experiment to measure this effect or not?
Sorry,
so
Ignacio, sorry to interrupt.
Yeah.
So is your previous statement related to the fact that anomalies are IR effects as opposed to UV effects? You don't get something that is, I would think that the Planck scale was something like the UV cutoff of your theory, but here you see that the anomaly is related to the IR.
Yeah. Those.
It kind of resembles that sort of.
Yeah,
statement.
I mean, I'm not exactly sure what you mean by the fact that it's an IR effect, but I would say the two coefficients that appear in the trace anomaly, the ones that we're talking about, are independent of the renormalization scheme.
So what I mean is that you get this these anomalies because when you renormalize, you're breaking the symmetry. But typically you mess up symmetries by renormalizing the UV, but the anomalies happen when you're renormalizing the IR. I think it's when you're removing divergences in the IR. But yeah, it's I'm
not sure about that.
It rhymes with that, but maybe it's not exactly. Anyways, yeah,
okay.
Just a comment. Thanks.
I'm actually not sure. Okay. Okay. So finally, what is the physical consequence or one physical consequence? So let's go back to the case of the Klein-Gordon equation. So we said you rewrite this equation as a Schrodinger equation, right? Like this. Phi equals omega squared phi, and there was some potential. The potential takes some complicated form, but the details are not important. The only thing that's going to be important is the following observation: that if you put L equals 0, so look at the S wave, right? In that case, you can evaluate the potential at the origin because the centrifugal barrier disappeared. That term is not there, so you can just evaluate the potential at the origin. And what you get, surprisingly, is that if you impose the regularity condition, smoothness of the metric at the origin, you see that the potential at the origin is proportional to, so minus the lapse function of the origin times the Ricci scalar at the origin. And I say this is sort of a interesting coincidence because there was no reason for you to get the Ricci scalar. You could have gotten anything else. In general, you're going to get something else. But you happen to get the Ricci scalar, which is precisely the object that we're able to calculate using the procedure I just showed. It's the only thing I can calculate exactly. As we just saw, the Ricci scalar takes this form. It has the classical contribution, and then there's the quantum contribution. So we already know how to deal with this. And yesterday, if you recall from yesterday, we saw that from the continuity equation, you could calculate, you could find the behavior of the lapse, so f at the origin, as you approach the Buchla limit. And we saw that we got an equation of this form for the fermions, where f at the origin is going to 0, so the redshift is going to infinity, when the central pressure goes to infinity. That was the whole idea behind the book telling. So what I'm trying to get to here is that we have these two contributions, so we can actually calculate this object. So the potential takes looks something like this. It's again trapping in the interior. That's always going to happen, and in the exterior is just a Schwarzschild. But now we're interested in the value of the potential at the origin. So for a second, let's forget about the quantum contribution. Let's just look at the classical, what this object would be at a classical level. Then you see that, and let's do a very simple example. Let's go back to the example where this is m squared square root of the rho. Okay, again, fermions. So now you see that what is the value then of the potential of the origin? Well, we need to multiply F0, which is given here, by the Ricci scalar, which is given here, right? But you immediately see that this square root of rho cancels with the square root of rho, and we get an m to the power 4, which is the only thing that survives. Apart from that, we have the Planck mass here. So, and notice there's a minus sign here. So what happens at the classical level? If we just neglect completely the anomaly, we get that the central potential is negative, and its value is given by this number over here, which depends only on the mass of the field and the Planck mass. What happens now if we include the anomalous contributions, or in other words, if the density increases? What happens is that now I need to put this term back, right? And because this term, again, grows faster than the classical term at high densities, this thing, as we just saw before, this makes the whole Ricci scalar change sign. Right? That was the whole point. And when the Ricci scalar changes sign, the central potential vanishes and it starts moving up. And then you're going to get, again, a set of quasi-bound states at some frequencies that you need to determine by solving some dynamical problem. But the point is, the main message is that the anomaly controls the sort of the spectrum of the low frequencies of the scalar field in this problem. This is a physical effect. And now we can finally ask the question, well, is this measurable? Well, one simple thing you can just think about to just estimate the order of this effect is the fact that if you completely neglect the anomaly, the value of the potential would be this number. Now, the potential vanishes at the critical density because then the Ricci scalar vanishes, right? So we can just ask, well, what is this value, right? That's just given by this number here. What's the order of magnitude of this number, which depends only on the mass of the particle and the Planck mass. So if you simply replace, replace, for example, the mass by the electron mass, this thing over here gives you, a frequency, because this is a potential, right? But potential goes like the frequency squared. So this gives you a frequency of something like 10 to the minus 1 seconds. This is essentially of the order of a second. So if you were an observer here very far away, if you could make an experiment to throw in or detect, in this case, scalar fields, scalar waves, and now you ask the question, if you look at the Oppenheimer-Volkoff problem where you really use fermions, then you have a prediction that there's going to be a set of frequencies that are going to be trapped in the interior that you're not going to see. This is like the absorption lines of the problem. And this frequency of that thing is order of seconds. So this is something that in principle you could measure. Okay, so that brings me to the conclusion. Can you still hear me? Because again, my camera...
Yes, we can hear you,
crashed.
but not see
cool.
you, I don't think.
Cool. Okay, so conclusions of today. The effects of the trace anomaly of quantum field theory. This is an effect that does not exist not even in relativistic quantum mechanics. A very simple computation shows that the trace anomaly becomes macroscopic in the sense that we discussed before, not at the Planck scale, but at a scale that is much before that is determined only by the mass of the field and the exponent appearing in the equation of state. And what happens is that the curvature of scalar simply becomes negative, and there's almost no room to vary or change anything in this calculation. We saw for the case of scalar perturbations of stars close to the Buchla limit, this anomaly controls the low frequency spectrum of the waves, such that it pushes the potential upwards. So somehow the object is becoming less attractive. As an outlook, I think two interesting questions are regarding the spin perturbations. So we looked at the scalar field, but looking at fields of other spin, I think is a really interesting question. And then the more general question of really how to relate this to dynamical gravitational collapse would be really interesting. Mr. Chairman, should I?
Yeah, sure. Yeah, we can. If you're ready, we have in principle 5 more minutes.
Do I have 5 more minutes or?
Well, in principle, the lecture is for an hour. Mariana, correct me if I'm wrong.
Yeah, I mean, you can leave some time for questions if you want, but
right. Yeah.
yeah.
If you're ready to wrap up, maybe do so. If not, if you need a couple more minutes,
right,
it's also okay.
Now, let me just leave you with one final idea that I think is super interesting. It's something I'm working on actively now, which is this case of the spinner, of the spin one half. I think this is a super interesting problem. So we just talked about the behavior of scalar waves in geometries close to the Buchla limit, but what about the behavior of spin one half waves? So the Dirac equation in curved spacetime is something that, unless I'm wrong, I think Fock was the first one to write this equation down. This is the Dirac equation where the covariant derivative, has the spin connection and then the gamma matrix is here. But there's a super interesting result due originally to Schrödinger 10 years after. What happens if you take the square of the Dirac equation in curved space? And the answer is different to flat space, because in flat space, the answer is you get the Klein-Gordon equation. That's how Dirac found it in the first place. But in curved space, if you take the square, what you get is the terms you would find in the Klein-Gordon equation plus a contribution coming from the Ricci scalar. But the Ricci scalar is precisely the object that is sensitive to the trace anomaly. As we saw today, it's the only curvature invariant that is sensitive to the trace anomaly. So there's a bunch of really interesting, there's a whole area of math dedicated to this. And I think this would be really interesting. Just to give you one example, if you take this equation and you basically integrate it by parts, there's something called the Lichnerowitz vanishing theorem, which applies to Euclidean manifolds without a boundary. So it's not exactly the case we're looking at, but it's somehow related. And it's an incredibly strong result. It tells you, if you have a manifold such that the Ricci scalar is always positive, it's positive everywhere, then there exists no solution to the Dirac equation, period. The simplest example, of course, is S2, the round sphere in 2 dimensions. There are no solutions to the Dirac equation. The Dirac operator has no zero modes in the spectrum, period. So I think the interesting part of the story is that what the anomalies are sort of affecting is precisely the Ricci scalar. And they're precisely telling you that this thing is going to change sign at some point. It sounds like it would provide some conditions to avoid the assumptions of the vanishing theorem. So it might lead to some interesting things. And more in general, there's the bigger picture of the fact that the anomalies is very well known that are related to index theorems and topology. So it seems that this is where the calculation is leading. I think it's a very interesting area, and I'll just leave that as a final thought for today. Thank you.
Thank you, Ignacio. We have some time for questions.